Hello, everyone. Our project titled Differential Privacy Algorithm for Privacy Preserving Data Analysis in the Modern Era. I am Koil, and my teammates are Manognya, Vanshika, and Kavan are joining me for this presentation. In today's world of big data and machine learning, organizations are collecting and analyzing enormous amounts of personal information to innovate, analysis, and make smarter decisions. However, this has created a serious conflict between data utility and individual privacy. Traditional privacy protection methods like data anonymization were once widely used, but they have proven insufficient against modern re-identification attacks. For example, in the famous Netflix price case, researchers were able to re-identify supposedly anonymous users by linking their movie ratings with publicly available IMDb data. This showed that anonymization alone doesn't truly protect privacy. To overcome these challenges, differential privacy, or it is also called as DP, was introduced by Cynthia Dwork and colleagues in 2006. Differential privacy provides a rigorous mathematical guarantee of privacy, which ensures that the output of analysis doesn't reveal significantly more information about any individual, even if an attacker knows almost everything else about the dataset. In simpler terms, the result of a differentially private algorithm should look almost the same whether or not a specific person's data is included. This makes nearly impossible to infer personal details from the output. What we will be exploring the foundational algorithms behind DP, such as Laplace and exponential mechanisms, and how these principles are applied in machine learning, especially through differentially private stochastic gradient descent, which is also called DP-SGD. We'll also be looking at how different companies like Apple and Google use differential privacy in large-scale real-world systems, and how combining DP with federated learning enables end-to-end privacy-preserving AI pipeline. Now that we have seen why differential privacy is important, let's look into the formal definitions, the mathematical foundation of why it makes everything so powerful. Differential privacy is built on the idea of neighboring datasets. These datasets that differ exactly one's individual record. For example, one person being added, removed, or having their data slightly changed. We define a randomized algorithm called mechanism, and that is denoted by M, that takes the data as input and produces some output, such as statistic or a model. The mechanism M is said to be epsilon delta, differentially private if the probability of it producing any particular output is almost the same, whether or not a given individual's data is included in the dataset or not. Formally, for all possible outputs or subsets of outputs represented by yes, for any of those two neighboring dataset D and D dash, which you can see in the next slide, the probability that M of D produces an output in yes must be most to the e to the power epsilon times the probability of M of D dash produces the output yes. So mathematically, this is how the formula looks. But in case the delta represents a tiny probability of failure, and there are guarantees that this delta would be equal to zero. We call it pure differential privacy, or epsilon dp, which provides the strongest possibility privacy guarantee. In that case, the epsilon delta will not be calculated. It will just stop with the S. Here, D and D dash are the neighboring datasets. M of D is the randomized output of dataset D. S is the any possible subset of data we are checking against. Epsilon controls the strength of privacy, whereas delta represents the tiny probability of failure. So this is how the data set looks.
Now that we have defined differential privacy mathematically, let's talk about the key properties that make it so valuable and practical in real-world applications. These properties ensure that differential privacy can be applied flexibly, even when multiple analysis or transformations are performed in data. The first important property is the composition theorem. It explains how privacy behaves when multiple differentially private algorithms are used on the same dataset. There are two main types of composition. The first one is sequential composition. When we apply several differentially private mechanisms one after another on the same dataset, say like M1 and M2 all the way up to MK, the overall privacy loss adds up. In other words, if each mechanism provides epsilon I and delta I differential privacy, then the combined result provides epsilon total and delta total, which is differential privacy, where epsilon total and delta total will be the summations of their individual values. This means that every time we release a new result from the same dataset, we are consuming part of the privacy budget. So we must track it very carefully. And the second one is advanced composition. Sequential composition can be overly conservative in estimating total privacy loss. The advanced composition theorem provides a tighter bond, showing that the accumulated privacy loss grows more slowly, roughly in proportion to the square root of the number of queries rather than linearly. Formally, for k mechanisms, each satisfying epsilon and delta, which is the differential privacy, the combined mechanism satisfies approximately, which is the formula which you can see here, for any small delta greater than 0. This result is extremely useful in practice, especially in iterative algorithms like training machine learning models, where we perform many small private updates. The next key property is immunity to post-processing. This means that once you have a differentially private result, no further processing, even complex or randomized computations, can make it less private. Formally, if M is epsilon and delta, then any function f applied to its output written as f naught m1 is also epsilon and delta. Intuitively, this means once privacy protection has been applied, it cannot be undone by analyzing or transforming the output later. This property is extremely powerful because it allows organizations to safely share or analyze differentially private outputs without worrying about breaking the privacy guarantee afterward. Finally, we have the concept of privacy budget representation by the parameter epsilon and delta. These parameters quantify the amount of privacy loss allowed. Smaller values of epsilon and delta provide stronger privacy, but usually introduce more noise into the results, reducing the accuracy. Larger values allow more accurate outputs, but with weaker privacy guarantees. So designing a differentially private system always involves balancing privacy and utility, protecting individuals while still extracting meaningful insights from the data. Core algorithms, core algorithmic mechanisms, global sensitivity and Laplace and exponential. Now that we understand the principle and properties of differential privacy, let's look at the core algorithms that make it work in practice. The first key concept is global sensitivity. Global sensitivity measures how much a function's output can change if we modify just one individual's record in the dataset. In other words, it tells us how sensitive a function is to any single data point. Formally, if we have a function f that maps a dataset into some numerical results, the L1, which is a sensitivity written as delta f, is defined as the maximum possible difference between f of d and f of d prime for any two neighboring datasets, d and d prime, datasets that differ in exactly one person's data. Mathematically, it is shown as this formula here, where L1 norm, meaning we sum the absolute differences across all components. So delta F tells us the worst case change in the output when one recording changes. For example, if we are simply counting the number of people who have a certain disease in a medical data set, changing one person's record can only increase or decrease the count by at one most. So the sensitivity delta F equal to 1. Once we know the sensitivity, we can use it to determine how much noise to add to protect privacy. That brings us to the Laplace mechanism. One of the foundational techniques in differential privacy, the Laplace mechanism is designed for numerical queries. where we want to release a numerical results like an average, sum, or count while preserving privacy. It works by adding random noise drawn from the Laplace distribution to the true output of the function. Formally, we define the mechanism as this formula, which shows m of d equal to f of d plus lap of delta f divided by epsilon, where each yi is random variable drawn from the Laplace distribution with scale delta f divided by epsilon. This means that the amount of noise added is directly proportional to the function's sensitivity and inversely proportional to epsilon, the privacy parameter. Smaller epsilon means stronger privacy, means more noise, and larger epsilon is weaker privacy, means less noise. The probability density function of the Laplace distribution is given by this formula, lap of uh, x given lambda equal to 1 divided by 2 lambda exponential minus absolute x divided by lambda, where lambda equal to delta f by epsilon. The remarkable result provided by Cynthia Dwork and colleagues in 2006 is the Laplace mechanism, which guarantees epsilon comma 0, which is differential privacy, often referred to as pure differential privacy. To summarize, the Laplace mechanism ensures privacy by adding just enough calibrated noise to hide the impact of any single individual's data while still keeping the overall result statistically useful.
So far, we have looked at how the Laplace mechanism adds noise to private and protect the privacy of numerical queries. But what if the query does not return numbers? For example, when we are choosing a category, a label, or a best option from the set of possibilities. That's where exponential mechanism comes in. The exponential mechanism is designed for non-numeric outputs, where the result comes from general and discrete set of possibilities rather than the numerical values. The key idea is that instead of adding random noise directly to the output, we use the utility function, often denoted by u of dr, to measure how good or desirable each output r is for the given dataset d. So this mechanism doesn't really realize all the data it selects in one output with the probabilities that depends on the utility score. Formally, the utility function u of dr assigns a numerical score to each possible result in R and to the output range, the capital R. Then we define the sensitivity delta U, which measures how much the utility score could change if one person's data in the data set were added, removed, or modified in a similar in the similar sensitivity concept we saw before. The exponential mechanism then selects the output R with the probability proportion to the formula that is given in the slide. In other words, the output with the higher utility scores are more likely to be chosen, but the selection process still re-aspects the privacy constraints that define the epsilon and the delta U values. Next, we'll be looking at how the differential privacy in machine learning works. We'll be focusing on the DP-SGD algorithm for now. So we would have understood how the differential privacy works at the algorithmic level. So we'll be looking at the machine learning level. The challenges of private ML training is the modern machine learning models, particularly the deep neural networks, are extremely powerful, but that power comes with serious privacy risks. These models can sometimes memorize details from their training data, especially when overfitted or trained on sensitive data sets like medical records or personal text. This opens the door for adversarial attacks where an attacker can query the model and try to infer whether a particular person's data was used in the training. One common example is the membership inference attack, where the adversaries determines whether a specific record was part of the training set. Even more concerning, in some cases, attackers can extract the actual sensitive data as names and personal attributes from the model's parameters. So, simply training a model on private data is not automatically safe. We need mechanisms that guarantee that no individual records has a noticeable effect on the model's final output. This is exactly what differential private stochastic gradient descent does, or the DP-SGD aims to achieve. So now the DP-SGD differentially was introduced by Adabai in 2016 in his paper. the standard stochastic gradient descent algorithm to provide the differential privacy guarantees during training. Let's walk through the main steps of the algorithm. The first one is computing the gradients. That is, for each example in a mini batch, we compute its gradients just like the standard SGD. Next, we will clip the gradients. Each individual gradient is clipped so that its L2 norm does not exceed the predefined threshold C. This ensures that no single data has an outsized influence on the model update. In other words, large gradients are scaled down so that every example contributes within the same bound C. The third step is introducing the noise. So after computing the average of these clipped gradients, we add the Gaussian noise drawn from the distribution with mean 0 and the variance proportional to lambda c square. The noise multiplier sigma controls the trade-off between the privacy and the accuracy. The higher the noise given stronger privacy can reduce the model's performance. The last step is updating the parameters. That is, finally, when the model parameters are updated using the noisy gradient, the process repeats for each batch in the iterations, ensuring that every update preserves the privacy. Next, once all of these steps are done, we'll be looking at how privacy analysis is done. So privacy analysis is guaranteeing that the DP-SGD is expressed in terms of sigma and delta, the differential privacies. To measure the control of total privacy loss over many training data, Abidi and his team introduced a moments accountant, a mathematical tool that tracks the privacy loss more precisely than the standard composition theorems. It works by bounding the log moments of the privacy loss to random variables. It follows the exact formula that is shown on the slide. This allows us to compute tight and realistic privacy guarantees even to the deeper learning models trained over many iterations. Now, when we look at the trade off, the most privacy preserving methods usually have the privacy utility trade off, which usually tells us that stronger privacy requires adding more noise, which reduces the model's accuracy. On the other hand, relaxing privacies improves the accuracy but weakens the privacy guarantee. Despite this trade off, Abidi and colleagues showed that the DP-SGD can still achieve competitive accuracies on standard benchmarks while maintaining meaningful privacy protections. In summary, the DP-SGD represents a crucial step forward towards the privacy-preserving machine learning models, allowing organizations to train models responsibly even on sensitive data without sacrificing the true trust in the compilers.
Having explored the theoretical and algorithmic foundations of differential privacy, let's now look at how these ideas are applied in real world systems and how they integrate with advanced learning paradigms like federated learning. For industry adoption, differential privacy isn't just an academic concept. It's already being used at a massive scale by leading organizations such as Google, Apple, and the US Census Bureau. Let's briefly look at how each of these systems implement differential privacy in practice. First, we have Google Wrapper. Google was among the first to deploy differential privacy at a global scale through their system called Wrapper. It is also known as randomized aggregatable privacy preserving ordinal response. Introduced in 2014, Wrapper allows Google to collect statistical data from user devices such as Chrome usage matrix without learning any individual's exact data. So, how does Wrapper actually work? It has two main steps. First is the Bloom filtering encoding. Each input value, say like a website domain or a configuration string, is converted into a bit vector using the Bloom filter. In simple terms, this means that each piece of data is represented as a fixed length binary vector, where a few positions are set to 1 according to hash functions. The second step that involved is randomized local DP. Then, in each bit of this vector is randomly flipped using a randomized response technique with certain probabilities P and Q. This introduces local differential privacy since the noise is added on the user's device before any data is ever sent to Google. The final vector, not the raw data, is what gets transmitted. This ensures that even the Google servers can't tell with certainty that what the original value was. Only the aggregate statistics across many users can be estimated. The second one we have is Apple. So Apple has also adopted differential privacy in its data collection systems described in their 2017 report, Learning with Privacy at Scale. Apple system gathers usage statistics from the iOS and Mac OS devices to improve features like emoji recommendations, predictive text, and lookup hints, all without exposing personal user data. They use algorithms such as the count mean sketch and the Laplace mechanism to add control noise to user data. For example, a user's frequency of emoji usage might be recorded, where Laplace noise ensures that any single user's input does not meaningfully alter the aggregated output. Apple enforces a strict privacy budget. Typically, epsilon is equal to 8 per day and epsilon is equal to 2 per individual use case. This balances privacy with the needful useful insights. The third one we have here is the US Census Bureau. A major milestone for differential privacy in public policy came with the 2020 US Census. For the first time, the Census Bureau used differential privacy to protect sensitive demographic data through a system called top down. This algorithm adds carefully calibrated noise to the population counts and demographic summaries released to the public. Importantly, top down ensures hierarchical consistency, meaning the numbers that still add up correctly across differential geographic and demographic categories, even though noise has been added. This marked a landmark shift in how government agencies safeguard the privacy of millions while maintaining statistical utility. Federated learning with the differential privacy also comes into place. For this, we have the following diagram. When we look at the most exciting frontiers, which combine differential privacy with federated learning, it was proposed in 2017. This model allows training to occur across many devices, such as smartphones, without transferring raw data to a central server. Each device trains a model locally and sends only model updates, not personal data. However, while FL provides some protection through decentralization, it does not guarantee formal privacy. An adversary could still infer sensitive information from these updates. That's where this comes into place. It combines the collaborative training of FL with the mathematical guarantees of DP, creating a robust privacy preserving framework. So here's the high level flow that we have. First one goes for local differential privacy, where each client adds Gaussian noise to its model update before sending it to the server. The clipping and noise ensure that no single client's update can reveal private data. Next, we have secure aggregation. The server aggregates the noise updates from many clients because each individual update is there, and even the server cannot reconstruct any client's local data. Then we have privacy amplification, which where the overall privacy guarantee improves as the number of participant client increases. A phenomenon known as privacy amplification by subsampling or the privacy blanket effect. This combination of DP and FL is becoming the gold standard for training models in sensitive environments such as healthcare, finance, and personalized device learning, where the data privacy is non negotiable. In conclusion, differential privacy has established itself as the golden standard for privacy preserving data analysis, offering rigorous mathematical protection that remains robust even against sophisticated attacks or the use of auxiliary information. At its core, the differential privacy is built on two fundamental algorithmic mechanisms. First, the Laplace mechanism, which is used for numerical queries where carefully calibrated noise is added to statistical outputs. Second, the exponential mechanism, which is used for categorical or non-numeric outputs, selecting results based on their utility scores. Together, these mechanisms form the building blocks for designing private systems that can balance data utility and individual confidentiality. When applied to machine learning, particularly through differentially private stochastic gradient descent, which is also known as DP-SGD, we gain the ability to train models that preserve privacy without severely sacrificing accuracy. This is a crucial advancement, allowing modern AI systems to learn from sensitive data such as medical or financial records while offering formal guarantees against information leakage. The real world adoption of differential privacy by organizations like Google, Apple, and the US Census Bureau demonstrates that this is not just a theoretical idea. It's a practical, scalable solution already operating at global scale. Looking forward, there are still open research challenges that will shape the future of this field. Some of them being that tighter composition theorems and improved privacy accounting methods will help reduce cumulative privacy loss in complex workflows. Efficient algorithms for high dimensional data remain an active frontier, particularly as models and datasets continue to grow in complexity. The integration of differential privacy with other privacy enhancing technologies, such as secure multi party computation and encryption, promises even stronger protection in collaborative or distributive settings. Finally, as data protection regulations like the GDPR in Europe and the CCPA in the United States continue to evolve, differential privacy is increasingly positioned as a cornerstone of ethical and compliant data analysis. In essence, differential privacy represents the future of responsible AI and data science, enabling innovation that is not only intelligent but also fundamentally respectful of privacy and human dignity. Thank you.